All right, moving on. So we proved this proposition. Let's look at an example of a quotient, and this is probably the most important example of a quotient. Let n be not equal to 0 or 1, then nz is a normal subgroup of z under addition. Okay, nz, of course, these are just multiples of n in z, and this is normal in z because, well, z is abelian. So any subgroup of an abelian group is normal. That's something that we proved, and so there we go. So we can take the quotient. So z mod nz is a group. So we can interpret this as the set from 0 to n minus 1 with composition law, addition mod n. And of course, this is a lot of information here. It's a lot of, oh, someone's having a party or something. So this is a lot of information, a lot of claims, a lot of stuff that hasn't been proven. At this point, I'm just going to assume that you've seen group theory before, and this is stuff that you would have covered. And so if you don't know this, then try to prove it. And if you can't prove it, then look in Michael Artin's book Algebra, or look in Dumbin and Foote Algebra. Those are really good first textbooks in abstract algebra. So this with composition law, addition mod n. Okay, time for a definition. A group G is cyclic if there is some element A in G such that for all elements G in G there exists some n greater than or equal to 0 such that we can write G as a to the power of n. So another way of saying this, let's see here. Well, okay, so this isn't n greater than or equal to 0. We want to allow negative exponents as well, so we take n in the integers, such that G is equal to an. We call we call the element a generator of G. Okay, now here we say a generator. Now you might ask, oh, is the generator unique? The answer is sometimes, usually not, but sometimes. Well, I shouldn't say usually not, because that implies that you have some sort of way of measuring how many groups. So you have to put a measure on a group, and I don't want to put a measure on a group. Or if I want to put a measure on a group, I want it to be a complete topological group, or like a Polish, I don't know, it's something. So fact cyclic groups are abelian. And, you know, I would prove this, but the proof only takes one line. And, I mean, where am I going to put the next line? I'm going to put it up at the top here. And so I don't want to have a proof where I have the statement at the bottom of the board and the proof at the top of the board. It just looks bad. The other thing is that it's really, really easy. Because what you do is you take two elements of our cyclic group, and you can write them as powers of a. So you can write one in the form a to the n, and the other one in the form a to the m. Then when you compose the two group elements together, what you get is you get a to the n times a to the m, which is a to the n plus m, but a to the n plus m is equal to a to the m plus n, because this addition is addition of the integers, and the integers form an abelian group under addition. And so that means that you can flip the orders and you get abelianity, abelianness. It's abelian. So let's do another fact. All cyclic groups are Z or Z mod NZ for some n greater than or equal to 0. And when I say R, I really mean R isomorphic to. But I don't know. I've had professors who consider isomorphic groups to be the same. I think most people just say like, okay, if you have two groups and they're isomorphic, we'll just call them the same. So anyways, cyclic groups are Z or Z mod NZ. Sorry that Z looks like awful. So suppose A generates G. So G is going to be our G is our cyclic group here. Okay. So if, and now I'm going to introduce a new term. If the order of A equals n, wait a minute, Z mod NZ. It's going to be Z strictly greater than 0. Oh, well, you know what? If we allow Z to be equal to 0, then this is going to work as well. Because if you let Z equal 0, or if you let n equal 0, then Z mod NZ is just Z mod the identity, the trivial group consisting of only the identity element. And that's, when you quotient by that, you get the group that you started with, and you can prove that. Anyway, the order of A, this is the smallest positive integer such that A to the n is the identity. And you can prove that such a thing exists. But anyways, if the order of A is n is finite, then G is isomorphic to Z mod NZ. If the order of A is equal to infinity, i.e. if there is no n such that A to the n is the identity, then G is isomorphic to Z. Okay, so that's that. So in terms of generators, you can prove that the both elements 1 and -1 generate Z. That's because basically when you're raising this to a power, like if you consider the integers under addition, then raising to a power means adding a thing to itself. So if you add, and not only adding it to itself, but because n is allowed to be in z here, you're allowing yourself to subtract from itself. So if you start with 1, if you can add 1 to itself and subtract 1 to itself to get anywhere in the integers, and so you'll be good. Same thing with -1, because you could just subtract it from itself to get back to 1, and then it's the same thing. It's the same argument. Of course, nothing else is going to work. If you look at 0, anything times 0 is 0, so you're not going to get all of z. If you take some if you take a positive integer, which is strictly greater than 1, let's call it n, then you can't get to n minus 1. So it's not going to give you all of z. Same logic goes for negative numbers. And how about generators? Or fact. Z mod nz is generated by any p in from 1 to n minus 1 such that the GCD, can I fit this, of p in n equals 1. So why is this true? I'm not going to write out a proof of this because I think there's a lot of details involved in this I really don't want to do, because I don't know, I don't like these types of problems. I don't really like finite groups. I don't really like finite things in general, groups in particular. And I know that's probably going to make a whole bunch of you out there who really like groups, you're going to like freak out and stuff, but I don't know, I'm much more of an analyst, and I like that stuff a little more. And so, I mean, like, this stuff is sort of interesting, but it doesn't really, I'm not really passionate about this. This is something that is kind of foundational knowledge for a mathematician. And so, it's sort of good for me to be going through these lectures because now I'm really learning this material well. But what I'm not learning well is the fact that z mod nz is generated by this, because I didn't want to sit down and have to work that out before shooting the video. I just wanted to go ahead and get to work. So what this really has to do with is, you know that the LCM of p and n is going to be equal to the product pn over the GCD, and so it's just the product pn. And so what's going to happen is that if you take some p whose GCD with n is equal to 1, then you're not going to get to a multiple of n until you multiply. You have to multiply it by itself n times to get to a multiple of n. And in doing so, all of the elements that all the numbers that you get when you mod out by n, all the numbers that you get are going to be distinct from each other. Because if any two were the same, then their difference would be a multiple of n or something like that. So it's basically, the argument is something along those lines, but I didn't work out the details. But I can, do I want to do this now? Yes, I do. Do the next one. Proposition. If hi, that's not hello, that's a collection of subgroups indexed by some indexing set capital I. If this is our normal, in parentheses, subgroups of G, then the intersection over all I and I of HI is a, of course in parentheses again, normal subgroup of G. And an interesting thing to note here is a lot of times when you're doing things like this, particularly for me being more interested in analysis, and like if you do arguments that kind of have this similar flavor but in measure theory, you have to worry about countability versus uncountability. And there's a huge difference between what you're able to do there. The nice thing about this is that I can be anything. I can be a finite set, it can be countable, it can be uncountable. Just any indexing set, doesn't matter the size, this will still hold. And so this is actually pretty powerful. Like you start, once you start getting down the road and you start seeing like all the problems that you can run into when you start considering doing something countably many times or uncountably many times, you start to appreciate when you have something like this where a statement holds over any indexing set I. So let's go ahead and prove this. So E is in HI for all I. So obviously when I say for all, I mean for all I mean for all little I and big I, but I'm not going to write that out. You know what I mean by this. Or at least if you didn't, then now you do. And now you'll be familiar with it when I just write this from now on. So the identity element is in HI for all I in capital I, and so E is also in the intersection over all I of HI. Okay, so that's good. If G1 and G2 are in HI for all I, then G1 times G2 is in HI for all I because it's subgroup, and so G1, G2 is in the intersection because it's in every single one. If G1 is in HI for all I, when I say G1 and G2 are in HI for all I, what I'm really saying is if G1 and G2 are in the intersection, then they're in HI for every single I, and so this and then so on and so forth. So if G1 is, let's just call it G. Actually, let's actually do what I was saying. If G is in the intersection over I of HI, then G is in HI for all I, and so G inverse is in HI for all I, and so G inverse is in the intersection over I, HI, and thus the intersection over I of HI is a subgroup of G. If HI is normal in G for all I, okay, so that's done. So we did the first part, and now we're moving on to the normality statement. So if HI is normal in G for every single I, let H be in the intersection over all I of HI, and G be any element of G. Then GHG inverse, well, we know that HI is normal in G, and so GHG inverse is contained in HI. That's what it means for HI to be normal in G. And this holds for all I, so GHG inverse is in the intersection over I of HI. But this holds for every single H in the intersection and for every single G in G. And therefore, the intersection over I of HI is normal in G. And yeah, there we go. This finishes the proof.